All right, welcome to today's lecture. Last lecture, we introduced one of the most important formulas in complex analysis, the Cauchy formula, which allows you to express an analytic function in a region as the integral over the boundary. Okay? So that's very important. And then we talk about singularities. There are different kinds of singularities. The basic concept of singularity is if at a certain point the function is not analytic, at that point is a singular point. So singularity in complex analysis is not the same as divide by zero, even though divide by zero is one of the singularities. Okay? All right, then we say, okay, there is the isolated singularity. Typically, this divide by zero is isolated. And then you have non-isolated. This branch point, some functions is non-analytic every single point. Give an example, right? All right. And then if it's isolated singularity, we say there's also two types. One is a pole. What is a pole? So essentially think of that. The most important thing is pole is related to divide by zero. So 1 over x, when x approaches zero, that's a pole at zero, right? So in complex analysis, 1 over z, that's a pole. What about 1 over z squared? 1 over z squared will be equal to 1 over z times another 1 over z. Then you should agree that we will agree 1 over z squared approaches, the denominator approaches zero even faster. So that's more, that means it's dividing by a factor that goes to zero even faster. That's a more serious pole, right? And we call it a pole of order 2 because it's z squared. And then we generally say a pole at z0 is a pole of order n if when this z approaches this point, it behaves like that. This is a function which is non-zero, attends to whatever value. The important thing is this factor here, this zero factor, z minus 0 approaches 0, is of order n. The order is important. So this is a pole of order n. So we introduce the concept. We can also say if you take the function times the zero factor to order n, the product tends to a constant. That means this behavior near the pole is whatever constant divided by the zero factor to power n, right? Therefore, it is a pole of order n. That's easy to understand. Singularities, the other type is called essential singularity. This guy, e to 1 over z, if you expand that in using Taylor series, you can see it has this 1 over z term to power n, but the n never ends, goes to infinity. Then that's an essential singularity. You cannot remove it or cannot regulate it. Okay. We went through the example. This is the summary table. Right? This is called removable because this function is analytic everywhere except for the point z is equal to 0. However, this function, when z approaches 0, has a well-defined derivative, which is 1. Therefore, why not just define the function everywhere else is itself, but at 0, exactly that point, we just define the function value as 1. And it turns out the whole thing is so smooth and as if there's no hole there. Okay? So that's removable. We learned that in real analysis too. Okay? And then a simple pole is of order 1 over 0 factor order 1. So 1 over z. So that's a simple pole. And order p is 1 over z to p. That's order P, right? This guy, it has essential singularity. You can never quantify it by a pole of a finite order. It's an infinite order, okay? So that's essential. And branch point here is analytic. It's not a pole, but it's a singular point, like 0 for this function and that function. And then there are some complex functions where every single point, the Cauchy-Riemann conditions are violated. That means every single point is a singular point. Okay. And again, these kinds of things, you do not see anything like that in real functions. Real functions, you have some region you can never reach. You have some place you cannot go there, like divide by 0. But it's very rare to find a function that you have an expression and every single point is not analytic. It's not essentially is cannot be differentiated. So that's very rare. Okay. But complex functions, that's a lot. You can make up all kinds of examples. All right, then let's talk about the other extreme, zeros. Of course, zeros and poles, they are the inverse of each other, right? Something goes to 0 is 0. Something divided by 0 causes a lot of trouble. So we also need to investigate zeros of complex functions. And the definition is just very simple. If f of z is a function of a complex function of z, when that function value takes on the value 0 at that particular point, z of 0, then we call that point a 0 of the function, or a root of the function. Okay, so in complex analysis, we say root is 0. Okay, it doesn't mean the location is at 0. It means at that location, the function value goes to 0. Okay. All right. Then we also want to quantify orders of zeros. Okay. If near that point, the behavior of the function is like that, which is a non-zero function times a 0 factor to order n. Then we call that 0 of order n. Very similar definition. The definition is similar to the pole definition. If we call it a pole of order n, it's not this times that, it's this divided by that. So just the flip of the pole, okay? All right, and then if the n is equal to 1, then that means the 0 factor is linear near the 0 point z0 there. We call it a simple 0, okay? So this is a simple 0. A simple 0 is the inverse of a simple pole. All right, so that's the poles and singularities. Remember this definition. This will come up again and again in the whole subject of complex analysis. Now, Taylor's theorem. If for a real function, I'm sorry, this is a typo here. What? I don't know what's going on. How do you...
Professor, tap again on that.
This thing? Oh, okay. Okay, yeah, thank you. Yeah, a real function is differentiable to any order at particular point x. Then the Taylor series formula is this. You learn this in calculus course, right? So function, we call it expanding into a Taylor series about that point. So essentially, you have a bunch of coefficients in front times this factor, x minus a, that goes from 0, which is a constant, and first order, second order, up to infinity. And it turns out the coefficient in front of each term exactly is related to the nth order derivative of the function at that point. But then you divide by n factorial. Okay. If you can prove that pretty easily, the point is that if you take that function, you do the first order derivative and let x tend to 0. The left hand side is f first order derivative x tend to 0. The right side, exactly only the first order f prime of a remains. All other terms just go to 0. So they are equal to each other. And you take that, do the second order derivative, go ahead and find that, again, the left side is second order of the function at a, the right side is also the second order of a. Only that coefficient remains, okay? So this is a very straightforward expression, actually. So now let's follow the idea and go to extend it to complex functions. We will say we can also expand an analytic function in the Taylor series form. The key factor here is still z minus z0 to power n, okay, similar to that. And then there is a coefficient in front, and it turns out that coefficient in front, the expression is very similar to that. It's just this. The nth order derivative of f at that point, expand the base point z0 here, divided by n factorial. So if you look at these two, they are exactly parallel. This is just an extension of this formula into the complex realm. Okay, that's it. All right. So that's that. How can we prove it? In fact, it's not that difficult. Okay, the whole idea is with the complex function, you can always use the Cauchy formula to express that as an integral, right? So this is the Cauchy formula. C is the boundary of analytic region, okay? So this function is analytic every single point inside C. And the Cauchy formula tells us that f at z can be expressed by this complex integral. The integrand here is f at the integral point theta, and then, not theta, this is cosine, okay, cosine minus z. This z corresponds to that. This cosine is all the integration point, okay, and divided by 1 over 2 pi r. So how do you prove? Remember, what we want to show is this guy will be equal to a sum of a bunch of things, essentially a polynomial of z minus z0. That's what we want to prove, right? That's the formula. So you want to ask your question, can I expand that into a polynomial of z minus z0? Well, let's see here. A very, very important, a very, very useful formula is the geometric series, which is this. 1 over 1 minus x. When x is smaller than 1, you can expand it into this. This is a beautiful formula. Essentially, it says, see here, this is a polynomial in x. All the coefficients are just 1. So 1 plus x squared plus x cubed up to infinity. And this series turned out to be exactly just this, which is very beautiful, okay? So 1 minus 1, 1 over 1 minus x. So what we want to do is, if we can somehow rearrange it so this x becomes x becomes z minus z0, that's what we want. At the end, we will have a polynomial in z minus z0, right? So let's do that. So what we want to do is, looking at this, we find that this is a z, which we need, but we also need a z0. So we will just z minus z0. If you do that, you need to put this back here to make it the same, right? All right, so this is equal to that. Now you can see I have this guy now. I want to show if I can make use of that to make the whole expression a polynomial in that. Well, I treat these as a constant, so I take it out. When I take it out, this is 1 over this divided by that is 1, and this becomes divided by that. So this, of course, you can see is exactly equal to that, which is exactly equal to that. But at that point, if you view this small fraction here as the x, we can use it. Okay, therefore, this constant is in front still there. This, we use the geometric series, it becomes a polynomial of this small fraction, degree n, add it together to forever, okay? Alright, if this is true, we will put this back in here. So f of z is equal to, according to this Cauchy formula, is this is from here, this is from here, and then the remaining is this. So we have that, and at that point, we already have what we want, because that's the factor I want to see a polynomial in that, which is exactly already it. So I just lump the rest together. That will be the coefficient a, in n, right? All right, so I keep this term here, which is this, and the remaining is expressing in that I absorb this into it. Or you can say, this I can, this one here, there is also the formula, the Cauchy formula for the nth order derivative. F of z is an integral. Fz over cosine minus z0. We also talk about the nth order one. So let me show you this. Where's the Cauchy formula? This one. Okay. So this is a 0 order. This is the nth order. So if you see this factor at the bottom, is linked to the nth order thing. That's exactly what we want here. Yep. Okay. So this thing can be written as the nth order of this. Then you need to put this n factorial here and this one, because the nth order here you have an n factorial there. Okay. And this is nth order. Therefore, this is equal to, this whole thing is equal to that. And these 2 by I and these 2 by I, this just cancel each other out. So if you view this as a, the coefficient a of n, that's exactly the Taylor series we are looking at, we are looking for. Okay? So at the end, we just show that if this function is analytic on this thing at the end can be expressed by a polynomial in z minus a z0, okay, from 0 off term up to infinity term, and the coefficient happens to be this, which is exactly, this agrees exactly with the real function Taylor series. Okay. All right, so that's Taylor series, very good. And then before I move on to the Lorentz series, there is also a very useful theorem. I'm not going to show the proof, just to mention that how unique it is. This is saying if you have a function, okay, you have two functions, f of z and g of z, they are both analytic in the same region R, which is this dark blue thing here. So the requirement is that the two functions are analytic there. And also, if there is a sub-region, you find that over this sub-region, every single point, the two functions are zero. No, not zero. The two functions are equal. Okay? So, however f, z changes, g will change exactly the same way. So these two functions are exactly equal at this sub-region of the big dark blue region. Then the theorem says this function has to be the same, has to be identical everywhere in that region. Okay? And again, this is, you don't see things like that in real functions. Essentially, what it says is you have two analytic functions in the same region. If you can show a line or a small rectangle or a circle, which is very small, a subregion of the thing, the two functions are exactly the same or identical in this small region. It's guaranteed that the two functions will be identical everywhere inside this big region. Okay? So sometimes it's a little bit difficult to imagine why is that? Why can I not define a function? Well, these two functions, yeah, I can define them to be the same on this smaller region, but outside I can make it different, right? You can do that. But if you do that, one of the functions of both will not be analytic everywhere. You need to realize that analytics is a very strong requirement. Any function that is analytics is very smooth. When you contour plot it, it looks very nice. Okay? If you make a function is analytic somewhere and arbitrarily change it, I guarantee at some junction points, connection points, they will not be analytic. Okay? But this theorem says the functions, the two functions f and g, they're analytic every point. That's a very strong requirement. It's exactly because of that. Whenever you have a small region, that region can be like this, can be a very small line. If a line is a region also, on a line, if the two functions is the same, the whole region, the two functions will be identical. Okay. So that's a very unique theorem and sometimes useful because you don't see that in real functions. I want to mention that. All right, now let's see if we have this concept, how can we get Lorentz series, okay? Okay, the Taylor theorem is wonderful, but it only works for functions analytic inside and also on a circle C. By the way, when we do this Taylor series, we need to make sure where, we need to understand where is the radius of convergence. Because the geometric function 1 over 1 minus x equals the sum of x n from 0 to infinity. That will only hold when x is smaller than 1. That means that function, that formula, the radius of that convergence is less than 1. Okay, so you need to make sure x is less than 1. Therefore, when we do the Taylor series, when we expanded the previous slide here, the implication is that this thing, this has to be smaller than 1. If this is smaller than 1, that means the radius of convergence is C. So all this formula will only work for points for Z inside C. Outside C, it may not work. Okay? So there is a radius of convergence here. Now, we want to also ask, what if inside C there is a single point of singularity? Will the Taylor series still hold? It will not hold. It will break down because remember the Cauchy formula we use to derive this require f to be analytic every single point inside C. Okay, so if there is a pole of order p at a certain point which is inside C, the Taylor series will not work. It will break down. Okay, all right. Then we ask the question that if we know there's a single pole inside here and we know the pole order which is p, is it possible to do something to get a series similar to Taylor series? Well, the answer is yes. That's what we will get called the Lorentz series. Okay, that's also a very beautiful way of handling singularity. Let's say we know at this point Z at 0, it is a pole of order p. Then that means when you times the 0 factor to order p times the function. When z goes to 0, you get a function which is analytic, right? Okay, which is also non-zero and analytic. All right, so we want to know what happened to this, but we do know this cannot be expressed as a Taylor series now because it has a pole there. Then we look at this, a new function, okay, which we call it g, because we know the order of p, we know for sure when this 0 factor to degree n times that, it gives us an analytic function. Because that's the definition of a pole of order p. All right? If that's the case, even though we cannot do a Taylor series for this guy, but we can do a Taylor series for this guy, right? Okay? All right, then let's do it. Now we will write it this way. And the coefficient, we just call it b of n. We know b of n is linked to b of z, okay? And b at the 0 order term cannot be 0. If this is 0, then you don't have that, okay? So this at the 0 order, the first term here has to be non-zero. Okay, so the argument, the argument is this. This is not analytic inside the whole region, but this is. So if this is, we can expand it using Taylor series, so good. Now if that's the case, but because this is equal to that, which will mean this whole thing is equal to that, right? This thing is equal to that. Then, if this is equal to that, we can divide this factor on both sides. So f of z is equal to g of z divided by 0 factor to degree n, which will be this. Because this is equal to that, so divide that. We will just divide it here. Now look at that. This is not a Taylor series, but it's similar. Okay? So we cannot get a Taylor series because of the fact it's not analytic at that point. But we can get something pretty similar. And this is a polynomial. That's also a polynomial. All right. Now let's then expand that and see what happened. Okay. So this is equal to that, and then I can write these out, right? The first order term z is equal to 0. So we have b0 times this to 0 and still divided by that. This does not depend on n. It's a constant here. That's the first term, or the 0 order term, the first order term, second order term, blah, blah, blah. And the p minus 1 order term, p order term, p plus 1, and then up, okay? All right, now something interesting happens here. So this one here, this is 1, right? So we have this. This is 1. This is p. Therefore, it becomes p1 divided by this p minus 1. That's just simple algebra, right? And this term here, you combine these two terms, it becomes p minus 2. And combine these two terms becomes 1, and these two terms 0, and these two terms on top 1, and these two terms on top 2. Right? That's simple geometry, but it is very, very interesting. You look at here, we have these factor at the bottom, and the order is reduced to 1 and then to 0, and then flipped to the top. The top now becomes z minus 0, and it's 1, 2, like that. And the coefficients here is b0, b1, blah, blah. Then, let's renumber the index. Because this is an order p on the bottom, we will not call it b0, we call it a negative p index. Because this negative p will correspond to that order, right? It's at the bottom. So this, we call it a negative, and then p minus 1. This p minus 1 corresponds to that. And this is, we call it a negative, p minus 2, and this corresponds to that. Okay. So that's just a notation thing, no problem. Okay. So we just shift the index by 0 shifted to negative p, so we have that. If after this notation change, we can then rewrite this whole thing into this, right? This then is the same as this one. It's just these B's are denoted again as A's with this index shift. So no problem, right? So now the whole expansion is this. And you compare this with the Taylor series, you see some extra terms there, which is those pink underlined terms. This is new. The green terms is very similar to just as Taylor series. Okay? So you have this pink term and this term. And this series, the first person that showed this or discovered this is called Laurent. So this is called the Rowland series. Okay? It's not quite the Taylor series, but similar. It contains actually the same Taylor series like terms plus something extra. Okay? All right, so let me rewrite this again. We have these pink terms, we have these green terms, and then we call those pink terms principal part of the Laurent series. These green terms, the analytic part. Okay? And this name is pretty obvious, because if you throw all these pink parts away, you got something like this, which is exactly a Taylor series, which is analytic, because every single term in this green part is analytic. So we call this analytic part, right? What about this? Of course, it's not analytic when z goes to z0. That's a singular point. But every single term, you can see here, quantified a pole of certain order. Right? This tells us this term corresponds to a pole of order 1. That's a simple pole here. The other term here is a pole of order 2. This is pole of order p minus 2. This is pole of order p minus 1. This is pole of order p. That's it. No more series than p. The most series pole is this guy. Is p. The highest order pole is p. Okay? Alright, so that also tells us this principal part controls the ring region immediately surrounding the singularity. If this is the singularity, when you get closer and closer, this is like a black hole here, okay? Things get pretty nasty. This is in control. All these terms just pretty much goes to 0. Right? That becomes insignificant. The closer to it, the more dominant this term is. The rest is just not important, because this will overwhelm the rest. When you go very, very, very close, only this term dominate. The rest just disappear. Or become insignificant, more and more insignificant, okay? Now, if you move away from that, go to towards the radius, the highest, the longest distance, or the farthest from the pole, this becomes more and more important. Because this is bigger, right? When this is bigger, you divide by something bigger and more, this becomes very, very small. So the significance of those terms will drop, these become dominant. But when you move closer to the pole, this becomes more and more dominant, the rest become insignificant. Okay? I think this is a very beautiful way to understand the behavior of analytic functions and poles. Okay? In the limit, when this tends to that, only this term matters. Because that's the highest order pole. The rest is insignificant. Okay? Also, I want to say here, depending on the nature of the points, z equals 0. The principal part may contain an infinite number of terms, so that if that's the case, the pole's order goes to negative infinity, or you can say, I should say, infinity, and the analytic terms also goes to infinity. So you have the whole spectrum. This n goes from negative infinity up to positive infinity. When n is negative, these are the poles. When n is positive, 0 or positive, these are the zeros, so to speak, okay? Or the analytic part, okay? So positive n's, all the terms will give you an analytic function. Negative terms give you pole behavior. Now, if you expand exponential function of 1 over z, you will find very easily that this whole order goes to infinity. So you will have this situation, okay? That's the essential singularity. So the order of essential singularity, if you treat it as a pole, is infinite. All right. So f of z has a singularity which is isolated, but is analytic everywhere else. Okay. So this is the troublemaker. Then the Lorentz series will converge in the region between the two circles. This C2 here is the outside region. This, make sure you limit the terms so the analytic terms will converge. Okay? The principal terms, they will converge because you are far away from that. They are not making any trouble. But what about when you get close to that? This puts a limit that says you cannot get into the black hole. Okay? You can move closer to it, but never go into it. So that's why the Lorentz series is interesting. The region of convergence is a ring, is a donut. It's not a pie, okay? The radius of convergence for the Taylor series is a pie or pancake, and the Lorentz is a donut, okay? Okay, about the singularities, I think I don't want to do it by hand because it takes too much time here. Let me just use this, okay? Alright, so we want to find the Lorentz series of this guy about singularities at two locations. One is 0, the other is 2. We have to do this separately, okay? So once we select 0, we expand everything into z minus 0. That's how you get the Lorentz series about that point. You can do that. And then once we select this point, what we need to do is looking into z minus 2 and make the whole function in terms of these terms, okay? So let's select this first. This 1 minus x, this is from the Taylor series, okay? 1 over z is already in terms of z to a certain degree, so no problem. We need to deal with that. This is z minus 2. What we need to do is we want to do z minus 2 and expand it into whatever coefficient times z to a certain degree. Add them together. Okay. All right. So for that, we borrow the Taylor series for this function. Now this is order 3, right? So this is 3. And you look up the math table. The Taylor series for that is equal to this. So we borrow that. First, you can say here, this is written as take the factor 1 over z out. We also want to make this 1, so we take the factor 2 out, which 2 cubed give us 8 is in front, and then this is 1 over, becomes z over 2 minus 1, and we flip it, so take the negative sign out, it becomes this. Once we are here, we can make use of that expansion, right? Therefore, we keep this, which is here, and this expansion here, whatever x becomes this z over 2. So it's z over 2. This x becomes z over 2 square, right? This x cube is z over 2 cube, blah, blah, blah. Once you are here, now you can spot the Lorentz series. This what is inside the parenthesis will be analytic. Is just the Taylor series of this. But now we have this 1 over z in front, so we need to put this in. So these times that we have this, these times that we have, actually this give us a constant term. This z cancels that, and these times that give us a linear z, this give us a square z, okay? Because this z cancel one of the z's here, etc. At this point, it is exactly a Lorentz series. You can see this is the principal term, right? 1 over, that's a pole. From here up, these are analytic. So these are, up to here, these are the analytic part of the function. This is the principal part of the function. And it reveals very, very clearly the order of the pole. What is it? What order? 1, 2, 3? 1. Here. Right? So it's a pole of order 1. And then we can then choose this one. When you select 2, now what you're after is you need to expand things into polynomial of z minus 2. Okay? This is already, then you need to do something about this guy this time. Okay? Alright. Next. This time is 1 over z, so we want to use this geometric expansion. Remember, this over that is equal to, if it's 1 over 1 minus x, it will be sum of x plus x squared plus x cubed. But if this is plus that, then the odd terms will be negative. The even terms still positive. Okay, so this is a Taylor series expansion of this, which is essentially the geometric series. And this time now, what we need to do is to expand things around 2. So we will do something of that. This z thing here, we will write it as, we can just call this a new variable cosine. We can keep writing z minus 2, but let's also write it as cosine. If that's the case, z will become cosine plus 2, right? So this will become that. Now you can see this is already the cosine terms itself. Now we need to deal with this, which we can make use of that. First, we want to make sure this is 1, so take the factor 2 out, so it's 2 plus this. At this point, we can make use of that. So cosine over 2, place the row of x here, and so plug this formula in. So this middle part becomes this. This 2 times cosine cube is in front. Once you are here, now you can see, you can time this in, you have this. The nature of this is exactly the Lorentz series. But this theta is now based on the point of 2 now, okay? So when we put this back on, because theta is equal to that, this can be written as this. Now you can see very, very clearly, these are the principal part of the Lorentz series. About point 2, these from here to the right, these are the analytic part. And looking at that Lorentz series, what is the order of the pole? The highest order of the pole? 3, right? The dominant part is this.
Can I go to the previous slide?
Previous slide. Yep. Okay, so you see here, this problem is very useful. It tells you when you want to select these 2 locations, even though it has 2 singularities, which one are you investigating is important. If you're investigating the behavior of this one, you need to do the Lorentz series about that point. If you want to investigate the behavior there, you need to do the Lorentz series about the other point. And you have 2 Lorentz series, okay? And here, there is one thing I like to say, very important. Of all these Lorentz series, it turns out one coefficient is the most important. Do you know which one? It turns out it's not the highest order one. It's also not any of these analytic one. It's the one that has the simple pole. The coefficient of the simple pole is the most important. Why? I'm going to show you later, okay? Because that term, that coefficient is called the residue. The residue is the term that will produce some result when you do a contour integral, a loop integral. All the other terms just disappear, okay? All right. That leads to a very famous theorem called the residue theorem. All right. So another way to get the residue is if you know the order of the pole, at that point you can get the residue, but just times the linear term to it. If you know the order of the pole, which is 3 at z here, you times that, you also get the residue, okay? This is a theorem allows you to calculate very quickly the residue or the a minus 1 coefficient in this way. This is faster, but you don't have the Lorentz series in this one, okay? The previous method, you have the whole thing. And why is the residue so important? Let me show you why. Okay, actually that will be, oh. The continuation of this lecture. Okay, all these is a repeat. All right. Okay, that's this problem. And here, now, let's see. At this point, we have some very useful and very advanced tool now. Any function we can deal with it as long if it's analytic. Easy, very easy, it's okay. Now, even though it's not analytic, as long as the singularity is not too bad. When we say it's not too bad, it's a pole. As I mentioned last time, a pole is well-behaved bad behavior. Well-behaved singularity. Pole, you can quantify that. You can manage it. Okay, let's say we have a function is analytic on C. Then the Cauchy theorem tells us integration of any loop, closed loop, will be 0. Right? Early on, a few lectures ago, we talked about that. And that comes from the Green's theorem on a plane. The 2D integral turns into a line integral that we talk about in engineering analysis 1. Okay, so that's it. Now, if f of z is not analytic, what happened to this guy? Of course, it cannot be 0 now. Remember, if it's 0 for all the loops, then you can prove if this is 0 or this holds for all loops, the function is analytic. But we are told it's not analytic now, so we want to know what happened. It turns out, remember this guy, 1 over z dz integrate over a unit circle. We did that explicitly. Okay, integrate it. Give us 2 pi I. And it turns out if that function is not analytic and it has one let's say f of z is still analytic, but this function here, z0 is inside. You can see this one. This guy is analytic. This is a simple pole, right? Because it's divided by the 0 factor linearly. So this is a simple pole. And the Cauchy formulas tells us if you do that, it gives you 2 pi I times the function value like this. This is from the Cauchy formula. Remember? The familiar form is f at 0 is equal to 1 over 2 pi I and then that. But move the 2 pi I to the other side. Alright, when you're looking at that, you start to suspect maybe we can do something if there is a pole. Because that's a pole, a simple pole, 0, that's also a simple pole. When we integrate it, we get these things. Yeah. So they seems very similar. Can we get something out of this? Okay. And the answer is yes. To do that, okay, so let me rewrite these again. Both integrand have a simple pole inside C. This simple pole is at 0. This simple pole is at Z0, right? We have two. This is simple pole at 0 at the origin. This is simple pole at this point, and we get this. It turns out, if you have other poles, even it's higher order, you will get something. It has to do with this 2 pi I times something. And it turns out that something is exactly the coefficient of the A minus 1, which is called a theorem, residual theorem. The residual theorem, there are many ways to prove, but I came up with my own way, which I think is very cool, okay? Let's just investigate this guy. Integration of a very simple function z to power n. That's a polynomial. Nothing can be more can be simpler than that when you integrate. Okay, so we know integration of z to n is equal to 1 over n plus 1 times z to n plus 1, right? Just raise the order of 1, and in front you have 1 divided by n plus 1. We learned that in real analysis. We can show, because when you do the derivative of this, you immediately get the integral. All is well, except we need to take care of something. We need to take care of not dividing by 0. This will work for all n's except when n is negative 1. When n is negative 1, we are in trouble, okay? Because this is 0, so we can't do it. And then, so we need to separate that out. When you integrate, this integrates z to negative 1, which means 1 over z, you integrate that. We also know how to do that in real functions. Integration of 1 over x is exactly log x, right? The indefinite integral is log x. So, in real function, in a complex function, it's similar. You integrate 1 over z, you will get log z. So now we have this equals either that or that, depending on the value of n. Okay, fine. Then now let's do something here. If we have a loop, okay, that loop encloses the origin here. And we start from point A, move all the way around counterclockwise and go back to B and then go back to A. So B approaches A. So we finish one loop. Let's see what happened, okay? So in the polar representation, Z about A is equal to R times e to I theta, right? We learned that. That's the polar representation of any complex number. So, okay. So we start from point A and trace the curve C counterclockwise and complete one turn, then we end up at Z at B, right? R is the same. These 2 points, they coincide, but the angle is different. Angle is 1 term, which is 2 pi. So angle changes from theta, becomes theta plus 2 pi. That makes sense, right? All right. So for n not equals to 1, let's see. If n is not equal to 1, we will have this. So the integration of this guy over this closed loop C here, okay, is from ZA to ZB. No problem, right? So integrate that. Immediately we get this, which is from here, okay? From here, then we put in the coordinate, we put in position from A to B, so it's ZB to this order minus ZA to n plus 1, right? No problem. And then we put this here, R is the same. For B, the angle is theta plus 2 pi. For A, is only theta. But don't forget this n plus 1, okay, which is from here. So this makes sense, right? And then what happened is, let's try to evaluate that. It turns out, because n plus 1 is also an integer, n is not equal to -1. So that's an integer. Integer times any 2 pi is a full term of the thing. It just gives us 1. So this guy is 1 all the time. So turn out this is the same as this one, as long as, because this is 1. So at the end, this is exactly equal to that. So the whole thing came about is because when you have a full 2 pi added to the argument or the angle, it does not change anything. So the value is the same, you recover. Actually, the value, this value is exact at A, at B is exactly equal to value at A. So they are 0. Right? So that makes sense. That means this thing, when you integrate for any circle is 0. Or the other way to look at it is z to n, if n is not negative, if it's positive or 0, of course it's 0, it's analytic. But the significance of this, even n is negative, like -2, which is not analytic. But after going this exercise, you can show it's also 0. Okay? If 1 over z squared, which is not analytic. But when you integrate that term about this closed loop, still is 0, just because of that, okay? So we know n not equals is different from -1. All these z terms you integrate will produce nothing. All right, now we need to deal with this guy, right? All right, this guy is 1 over z. So now you go from ZA to ZB. This is equal to log of z, right? So we have ZA to ZB. So it's log ZA minus log ZB minus log ZA, which means log, this is B, ZB, this is ZA, and we know log of this guy, we have log of R, and then this to that, just give the exponent here, I theta plus 2 pi, and this here we have log R, and this here we have this I theta, right? Because log and exponent, they cancel each other out, only whatever exponent here remains. And then this log R, of course, is equal to this log R, they cancel each other out. This I theta cancel this I theta. Now we have a 2 pi I remain. This one. Right? Of course, that's not surprising. We spent half a lecture to do this integration, remember early on? By doing it carefully around a circle, we get 2 pi I. And here we do it this way, we also get 2 pi I. Right? So, now we have the very important result here. When you integrate z to power n, you will get 0 as long as z is not -1. Okay? If z is -1, you don't get 0, you get 2 pi I. This is very, very important, okay?
So why did we do that, like half of lecture doing this and that method? This is very easy and shortcut.
Yeah, you can do that, but sometimes you can approach things from different angles, so you have deeper impression of things. Okay? All right? Now, let's see what is the consequence of this. Let's say f of z has a pole at z equals 0, then, and in order p, okay? Then we already saw we can expand that into a Lorentz series. We have this principal part here, the highest order pole is p, and then we have p minus 1, p minus 2, blah, 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 and 2, and then 1.